conferencia de emisiones de NT, estrategias de filtración y soluciones de rendimiento. Me voy a permitir presentarles al señor Gautam Marwaha. Él es gerente regional de productos de Canfield Power Systems. Esta empresa tiene su sede en Laval, Canadá, o más. Gautam cuenta con más de una década de experiencia en tecnologías de filtración de aire para turbinas de gas. Se especializa en el diseño, la evaluación del rendimiento y la optimización del ciclo de vida de los sistemas de filtración para turbomaquinarias. Gautam también cuenta con una maestría en ingeniería mecánica y MBA. Su trabajo fusiona un profundo conocimiento técnico con la planificación estratégica y analítica para respaldar a los equipos de ingeniería, operaciones y gestión de activos. Su objetivo es desarrollar estrategias de filtración que mejoren la confiabilidad y la sostenibilidad de la disponibilidad operativa en las flotas de turbinas de gas. Bienvenido. Adelante, Gautam. Un aplauso, por favor.
Hello everyone. So, our host already introduced me. My name is Gautam. There should be subtitles there, so just give me a second, I'm going to fix that. It's working. Oh, okay, it's working. So, I think we are a kind of cozy group, so I know this is a presentation, we're going to talk about a lot of different things. Once it starts.
Por favor, tenemos dificultades técnicas con la traducción. Un momento, continuamos.
Okay, we'll check again. Perfect. So it works now. And I have the clicker, so I can forward. So, as I mentioned, I only speak English and very, very poor Spanish. I'll try to speak really slowly, so it's clear for everyone. Just by a show of hands, how many people understand English? Okay, so we have a few people here. Perfect. At any point, if you find that I'm going too fast or you have a question to ask, I have some colleagues here. I have Jose in the back and Antonio. They're perfectly fluent in Spanish and English, so they can help us with any of those questions. So today we'll talk a little bit about how you can use air filtration, good quality air filtration, to reduce the emissions of gas turbines. I don't know why there's echo now. Is it okay? All right. So I won't go over my introduction again. My role in the company is also a product manager. I take care of Americas in Canfield Power Systems. I'm really happy to talk to you about filtration. Really, when you look at our office, when you look at our people involved in this division, we're really passionate about air filtration. Is it better now? Okay. So yeah, during this presentation, if you have any questions, feel free, we'll talk about it. After this, if you have any questions, I'm really happy to talk to any of you at any point. A little bit, our agenda for today. I'll begin with a brief introduction about Canfield Power Systems, about air filtration, what we do. We'll then talk about some methods by which we can reduce emissions for gas turbines. We'll also look at some of the latest standards that are applicable to air filtration for gas turbines, and that's really important. Then we'll look at some strategies on how you can reduce your emissions, some strategies for legacy systems, older systems, and finally we'll talk about remote monitoring and what you can do and how you can monitor your assets to make sure they're running the way you should. So briefly about Canfield, it is a family-owned business. They've been in air filtration for about 60 years. The company is headquartered in Sweden, in Stockholm. We have 5,700 plus employees, I think close to 6,000 people globally now. We have manufacturing in about 30 locations, including 8 locations within North America. So if we're looking at Mexico, it's a lot of different factories here that can support any of the needs locally. We also have 6 R&D centers, including 2 in North America. I'm based in Laval, where we have one of the R&D centers for power systems for turbo machinery. We have another one in the US. So that's where we do a lot of the research, a lot of the product development for all these different products for gas turbines for turbo machinery. And of course, we are based in 35 plus different offices globally. So no matter where you are, what kind of asset you have, if you have any issues, you can reach out to me or one of my colleagues. Somebody will be there to support you with any of your needs. Camphil Power Systems that I belong to is a division of Camphil. And this division of ours, we specialize primarily only in turbo machinery applications. So we're looking at gas turbines, generators, diesel generators, different kinds of compressors, all of those, we take care of that through power systems. And our expertise includes everything that you see on the screen there. So we produce everything from the filters, to the filter houses, to the ducting, the enclosures, the exhaust systems, everything else, we take care of that. Everything, like I say, everything connected to air that goes into the turbine or out of the turbine, we have some product that falls in that category. So, big question, that's why we're all here. How can we reduce the carbon emissions, the emissions intensity of your assets? So, before we get into that, just by a show of hands, how many people here work with or work at the plant directly? Okay, so we have 2-3 people with that. How many of people here are aware if their organization has some kind of carbon emissions reduction target, or if your organization has an emissions reduction target? Okay, so everyone, would you mind sharing what your target is?
Well, we don't have like a set carbon emission, but we are working on a target. So we're trying to build a target for 2050, and we're exploring some opportunities. So that's why I'm here.
Thank you for sharing. So throughout the presentation, sometimes I'll point to people and ask questions. Don't be shy, don't be scared. Like, you're really nice to participate. So it's when we all ask questions, when we all answer questions, we all learn something new. So, looking at means of reducing the carbon footprint, your emissions. There's 3 primary ways you can do that. The first one is you can use fuels that are less carbon intensive. So if you look at power generation, now a lot of the examples that I'll talk about will be related to gas turbines and power generation, but all of those also equally apply to other turbo machinery applications. If you're running a large compressor, if you're using another turbine to run a big pump or a big compressor, depending on your industry, all of these things still apply. So when we look at power generation, if you look at emissions from coal, really high emissions, right? That's why everywhere there's a focus on reducing coal power electricity generation. As you switch from coal to natural gas, already you see a big reduction in your emissions. So you are producing somewhere around 390 kilograms of carbon dioxide per megawatt hour. However, if you go to even more carbon neutral fuels or fuels that have lower carbon footprint, if you can mix some hydrogen in there, which is a big focus that a lot of the turbine manufacturers are looking at. For example, if you add in some blue hydrogen, you can reduce that number from 390 kilograms to 365. If you get green hydrogen instead, you can actually go to even lower numbers, you have even lower fuel intensity. Is everyone here familiar with blue, green, gray hydrogen? Okay. I'll just quickly cover for anyone who's not sure. So depending on how you produce the hydrogen, so if you produce hydrogen using renewable energy, it's called green hydrogen. If you're using it through catalytic means or by natural gas or other means, then you're looking at blue hydrogen or gray hydrogen. And if you can switch your fuel all the way to 100% hydrogen, which some OEMs are claiming that their engines can do, although the infrastructure is still kind of in development at this point, you can bring your emissions all the way down to a really low number. You're looking at 25 kilograms rather than 390 or so. So 1/8 the emissions that you would look at otherwise. The other way you can reduce your emissions and your carbon footprint is with your existing assets. Or you can either buy engines or you can have assets that run more efficiently, so you're using less fuel to produce power. Or if you have existing assets that you do not want to replace for any number of reasons, you can choose to run those assets more efficiently. So either you buy more efficient engines or you run your existing efficient engines more efficiently. So what does that look like? Again, I'm using the example of gas turbines, but the conclusions are applicable in other locations as well. When we look at the gas turbine technology that has evolved over time, newer engines are more efficient. They're also more sensitive. We'll talk about the sensitivity in a couple of slides. But the big gain when you go to newer engines, for example, if you're going from an F-class engine to an H-class engine, you're getting a reduction in your heat rate. Your heat rate is the amount of fuel you burn to produce 1 unit of power. So typically we'll mention that in megajoules per megawatt hour or kilojoules per kilowatt hour. The numerical value remains the same. So when you go from an F-class engine to an H-class engine, you're doing that because you want to get a more efficient engine, which is more efficient at burning the fuel to produce the power. So you have a lower heat rate, and that reduction in heat rate is about 1.6%. So keep that number in mind. Now, if you're building a new power plant, for sure, you can look at buying the most energy efficient engine out there, using that in your assets. However, if you have an existing plant, you have existing assets, you can choose to look at options to run your engine most efficiently or as efficiently as possible. So when we compare that F-class engine and H-class engine, where you're getting that 1.6% improvement in heat rate, that benefit can quickly go away if you're not using the right kind of air filtration for that engine. So that's the example that we're showing here. If you look at this graph on the right-hand side here, if you look at that H-class engine, which has a lower heat rate to begin with, but you use slightly lower efficient filtration, slightly lower grade filtration there, a T9 class filter. Don't worry about the standards, I'll talk about those in the next slide, so just bear with the numbers for the time being. If you're running that H-class engine with a lower efficiency filter, you're going to get a lot of performance degradation, which will bring the heat rate of that newer, more efficient engine to the same level as an older F-class engine in only about 4,000 hours. So in a typical environment, at about 4,000 hours, your heat rate of your H-class engine is the same as an F-class engine, but that is running a better quality filtration, so it's protecting the engine a little bit better, you're seeing less degradation, and 4,000 hours is just half a year. So you spend a lot of money in buying a new engine because it's more efficient, you get lower heat rate, you have less emissions intensity, but all that benefit can be quickly eroded if you don't have adequate protection for that engine. In just about 6 months, it's not performing the way you expected. And throughout the rest of the slides, we'll cover what you can do to make sure that it is running the way you want it to. And the last thing that you can do to reduce your carbon emissions is carbon capture and storage. This is something that is still kind of in the very early nascent stages. It's being explored. In the US, we've seen there was a big push for it in the last couple of years. With the newer administration, it's not so much the primary focus anymore, but still something that is being actively investigated. Nothing has been made to scale yet, so for large power plants, for combined cycle power plants, if you are running large turbines, a solution does not exist yet. So your best bet with the current technology is either to use fuels that have lower carbon intensity, to have assets that run more efficiently, so you're looking at more efficient engines, or to run your existing assets as efficiently as possible. So earlier I talked about the impact of filters, how if you have low efficiency filters, they don't protect your turbine, and your performance goes down, your heat rate goes up. So how do filters impact that? I'll briefly talk about Scope 1, Scope 2, Scope 3 emissions, just for people who are more familiar with these terms. everybody here kind of understand what scope 1, scope 2, scope 3 are? So, scope 1 emissions are emissions directly related to your product, to a certain product that is being produced. So for example, in context of filters, this is the impact of all the raw materials used to produce the filters. So directly related to the filter production itself. Indirect emissions, this is related to scope 2 emissions or indirect emissions. You're looking at the carbon intensity for all the energy requirements to produce the filters. So if you're producing these filters in a factory that is using electricity from a coal-fired power plant, the carbon intensity of that electricity is quite high, so scope 2 emissions are going to be quite high. Conversely, if you're using renewable electricity to produce this, scope 2 emissions are going to be low. And finally, you have scope 3 emissions. These are also indirect emissions. These are not related to the production of the product itself, but how the product is used. And in context of turbo machinery and gas turbines, this is the one that is most significant. So if you look at the overall emissions related to filters, 4% are related to fabrication, production of the filter, 3% are related to processing the residues and so on. 93% is related to the use of the filters. And when we look at the use of the filters, because we're talking about turbo machinery, we're talking about the emissions intensity of the gas turbine itself. So this is how filters kind of play a role in your overall emissions intensity. Next we'll talk about where exactly do the filters come in, how exactly are they impacting the performance of the turbine. So I see a couple of students here. You guys should be more familiar with the Brayton cycle, with how a gas turbine works. I'll still give you a recap. So what we're doing in the turbine is we are ingesting large amounts of air. We're compressing it to high pressure, mixing it with fuel, combusting that fuel. As the expanding gases go through the turbine section to the hot section, they turn the blades, which might be connected to a shaft, which can be connected to a generator to produce electricity, or you could connect that to a pump or a compressor to get some useful work out of the turbine. So everyone's familiar with this part. If you think about what's going into the turbine, 98% of that is air. So 98% of everything that the turbine is ingesting is actually air. And that's where the air filters come in. When you look at the ambient air around you, there's lots of tiny particles. There can also be a lot of chemical contaminants depending on where you are. So even in this room, for example, it feels relatively clean, but we probably have a lot of tiny submicron particles that we cannot see. And when you take into account that 98% of what's going into that turbine is air, even that small particle has a big impact on the overall turbine performance. So how exactly does that work? There's 5 primary ways in which filtration or the lack of filtration impacts the performance of turbines. First up, going from left to right, you have what we call foreign object damage. This is usually caused by large items, not really tiny particles. So if you are a gas turbine operator, and if you've ever experienced this, really sorry for you. Typically, we see this nowadays when someone's doing an inspection and they've left behind a little pen or something, or there's some loose fasteners, some nuts and bolts that are left behind that somehow make their way to the compressor to get that catastrophic damage. Of course, when that happens, you have no choice but to replace the components to get it working again. As we move from these large objects to actual particles that cause damage to the turbine, we have erosion. So when you're looking at particles in the 5 to 10 micron range, the turbine blades, the compressor blades are rotating at a very fast speed. So at that speed, when these small particles, only 5 microns, when they hit the blade, they can actually remove some material. So the impact is effectively sandblasting them. You're removing material, so it is non-recoverable degradation. The only way to get your performance back, again, is to replace the components during a major overhaul. And that's how you get your performance back. I'm talking about microns in terms of particle size. Is everyone familiar with what a micron? Anyone want to guess what or tell everybody else what a micron is? So 1 micron is 1/1,000,000th of a meter. If you look at some average things to compare size by, a typical human hair is anywhere from 70 microns up to 100 microns. My hair is thin, so it's probably at 70. The human eye, we can see things, if you have really good eyesight, you can see down to maybe 25 microns, 30 microns. So everything that we're going to talk about from now on is invisible to the human eye. These are not particles that you can see, so you cannot walk into a site, into a plant and simply, hey, the air looks clean, I don't see any dust, so it's probably clean. That's not the case. All of these are really, really tiny particles. So, particles that are 5 microns to 10 microns can cause erosion, which is, again, non-recoverable damage to the turbine. We need to replace components to get our performance back. Thankfully, that is very easy to solve. Even the most basic filters nowadays will be able to take care of erosion, so that's not a problem anybody should be seeing anymore. As we move to even smaller particles, if you have certain chemical contaminants in your site, if you have salt, so either sodium chloride or other kinds of salts, you can have corrosion. This corrosion can take place both on your hot end, on your cold end, and also just the general construction of the air inlet system. This happens because the salt combines with the sulfur from the fuel, which we typically see in sour fuels, and then again, non-recoverable form of degradation. If that happens, very commonly we'll see that in coastal areas and offshore areas. When that happens, again, you have to remove the components, replace the components, take major corrective action to get your site running again. We go down to particles in the 2 micron to less than 2 micron range. There we can see impact in terms of plugging up of cooling holes. So these impact the heat transfer of the blades themselves and therefore change the performance of the unit. And then we also see fouling. Fouling is the most common degradation mechanism that you'll see, that we see when we look at the field data, and that's the one that most commonly people talk about when they talk about their units, their performance degradation, their operations, and so on. So what fouling is that all these super tiny particles, when they get to the blade is rotating at a fast speed, they stick to the blade. When they stick to the blade, they're changing the aerodynamic profile, so the blade is not functioning the same way that it used to. It impacts your mass flow, it impacts your other properties, and this will result into performance degradation in terms of reduced power output, increased fuel consumption because your efficiency is going down. And there's plenty of studies to actually talk to understand how much fouling impacts different kinds of turbines depending on what level of particulate matter makes its way to the turbine. So here's one study. This was conducted by GE and Alstom. It's on, I think, 12 different turbines across many different countries. And what they tried to track was, depending on the kind of filters that you use, so that's the first column there. You see the numbers F8, F9, 10, 11. Those relate to filter classes. We'll talk about those in a couple of slides, so don't worry if you don't immediately get those. But they track the engine performance using this kind of filtration to stop all these small particles from getting to the turbine. And they track that over a period of time, what was the impact on the performance. So on the low end of filtration, on the F8 class filtration, you were seeing almost a 7% drop in power output and almost a 2% drop in compressor efficiency after just 1 year. As you improve the filtration, going all the way up to E11 in this case, that number drops from 7% to just about 1% for power output and below about 0.3% for compressor efficiency. And since we're talking in context of emissions, what does that mean? If your compressor efficiency is going down, it literally means that it's not as efficient, it's not running as efficiently as it can. So you're burning more fuel to produce the same amount of power. Your compressor is taking more useful work out of your gross work done by the turbine, and therefore your net power output is going to be lower, but you're still burning the same amount of fuel, so your heat rate is going to go up. And if you look at this relationship here, you're losing, on average, about 3 to 4 times the compressor efficiency and power output. So when you have about 7% reduction in power output, you have about 1.8% reduction in your compressor efficiency. So keep this relationship in mind as you look at the next couple of slides talking about the impact of filters and how you can use those to improve your emissions. Any questions so far? Perfectly clear for everyone. Alright. That's good. I mean, even if you have any questions after this, feel free to reach out to us by email or my colleague here, Jose or Antonio, and we'll be happy to answer any of those questions. So, going back to carbon emissions, if your heat rate goes up by 1%, that means you're using 1% more fuel per megawatt hour per unit power, which also means you're producing 1% more carbon emissions per megawatt hour. So it's very directly linked. When you look at a lot of other things, you have to kind of understand the total impact that if I have a certain impact of my asset, of my product on the turbine, you have to go through a bunch of different steps to understand what's happening in terms of your emissions. But here it's super clear. 1% reduction or 1% improvement in your heat rate means 1% less power, less fuel consumed per unit power, which means 1% less emissions. Or conversely, 1% more emissions if your heat rate is going up. In context of filters, how does that come into play? If you have low levels of fouling, low levels of corrosion, and you have low levels of filter pressure drop. So we'll cover this aspect in the next two slides as well, all the different aspects of filter performance. If you have low level of fouling on the unit because of high efficiency filters, you have low pressure drop and stable pressure drop because of the performance of the filters themselves. That means you will have less fuel consumption, lower heat rate, and therefore lower emissions. Try to understand quantify the amount of emissions reductions we can get. If you go from a T8 class filter to a T11 class filter, usually when you're looking at the standards, the number is kind of an indicator of the efficiency. Lower the number, lower the efficiency, higher the number, higher the efficiency. So going from T8 to T11, we're going to higher efficiency filters, which means you're stopping more particles from getting to the compressor, from getting to the turbine. That can lead to about a 4% increase in power output. So this was a study that's published in ASME, it's done across multiple different turbines as well. Now there's multiple studies that have confirmed these kind of values. You get a 4% improvement in your power output. So from an operation point of view, if you're a power plant and you want to produce as much power as possible, or you're providing power for some critical application and you want to have as much power as possible, that is important. But in context of carbon emissions, your heat rate also decreases. So by increasing your filtration, you're preventing degradation of performance of the turbine. You're improving your heat rate by 2%, which means your emissions are reducing by 2%. Which means your overall targets are closer to meeting them. If you look at this kind of improvement and you see what can be gained across your entire fleet, so here I have an example of the US, but you can replace the numbers with your fleet and you get similar numbers. So in the US, about 1,800 million megawatt hours of power are produced annually. This number is from 2023. That amount of power production led to about 700 million tons of CO2 production. Going from this filtration class, from T8 to T11, if that was to be done on all this entire fleet, assuming the entire fleet was T8 class and now we move it to a higher efficiency filtration system, we can get an improvement of about 14 million tons. So already a big number when you're looking at your overall targets. That's just the impact of filters. And to combine it with the previous things that we talked about in terms of using less carbon intensity fuels, if you were to move that to natural gas and 30% hydrogen, you can get 46 million tons of reduction. And if you were to move it to 30% green hydrogen, you can get 75 million tons of carbon reduction. So the big question for anybody running different turbines at their site or potentially looking to set up new power plants or new capacity, what is the most cost-effective way for you to achieve your emissions target? Is it to buy newer units? Is it to look at carbon sequestration? Is it to look at different fuels? Or is it to invest in the current setup as well and making sure it's running as effectively as possible by investing in good quality air filtration? Any questions so far? Am I speaking too fast? Is it okay? And Jose, are the subtitles fine? So we have a couple of case studies to talk about how we've seen this reduction in real life, including some from the region, some from other parts of the world. So our first one is from Thailand. This site had 38 GE gas turbines, not big ones, medium-sized, small-sized gas turbines. We upgraded their older units, their legacy systems, to higher efficiency filters, T10 class filters. The original was T10, we upgraded them to T12 class filters, slightly deeper filters. That's not as relevant at this point. But what that led to, that improvement in filtration efficiency, that gave them savings of more than $500,000 per unit per year. So you multiply that by 38, because there are 38 assets at site. That's a big amount of number. You're looking at $19, $20 million in savings annually. It also gave them 166,000 MMBTU reduction in fuel per unit per year. So big amount of reduction there, which led to about 8,800 tons of reduction of carbon per unit per year. So again, if you're looking at a fleet level target, if you're looking at overall operations, you have multiple assets, or you're looking to build a new capacity, all of this can be really helpful towards achieving your emissions targets. So up until now, I've talked about the impact of filtration. So there's 5 main degradation mechanisms, how they impact the performance of turbines. Then I talked a little bit about how if you improve the filtration, you go to high efficiency filters, you remove some of those impacts. And then I mentioned some different filter classes like P8, P10, F9, F8. It can be quite confusing, so let's talk a little bit about the different standards that are used to classify filters and give you these filter classes. So just by a show of hands, how many people here are familiar with ASHRAE or EN standards? No one? All right. So very often when you're looking at filters, they will be specified by using an ASHRAE standard, ASHRAE 52.2, or an EN standard, and you'll get a filter class like MERV 16 or F9 or ISO EPM1 60%, which sounds really complicated. All of those come from different filtration standards. What a filtration standard really is that you take a filter, you put it in the lab, you put it in a test tub like the one that you see there, you throw some dirt on the filter. You see how many particles were upstream of the filter and how many particles made their way past the filter on the clean side. When you do that, you can calculate the efficiency. You can look at the efficiency by the size of the different particles. And with that, you can compare it to the classification table according to a standard and get a filter class. And when I talk about filter standards, all these ASHRAE standards, ISO 16890, EN standards, these are not really meant for turbo machinery applications. They come from clean room applications or heating, ventilation, air conditioning. I mean, ASHRAE is literally American Society for Heating, Refrigeration, and Air Conditioning Engineers. So it's not specifically turbo machinery. In the past, they have been used because we did not have a standard for turbo machinery. But now we have a new standard that is specific to gas turbines, specific to turbo machinery, and addresses all the different aspects of performance relevant to turbines. And that is the ISO 29461. And here's an example of how the standards can be confusing and how the new standard, which again is specific to gas turbines, helps remove some of that confusion. So I have 2 filters here, filter 1, filter 2. They are both rated MERV 16 according to ASHRAE 52.2. Because they have the same rating, normally you would expect the same kind of performance out of them. But if you look at this column in the far right, this column here, you can look at their efficiency against small sized particles. So if you remember earlier, I mentioned we were looking at the degradation mechanisms, and fouling, which was small particles, was causing a bunch of that. That filter is only about 34% efficient against that, meaning 66% of the particles are going past the filter, compared to the second one, which is also MERV16, but only 3% are going past the filter. So it's 22 times more efficient, but they have the same ASHRAE rating. And that's why ISO 29461 exists, so we get more differentiation. Look in the second last column, one filter is rated T5, one's T10, so the differentiation is far clearer. It's actually a lot more involved than what we have time for right now, so I'll just address some of the other filtration parameters briefly, and then we'll go on to some more case studies. So the other aspects of filtration-specific performance, of gas turbine-specific performance that the new standard addresses is things like your dust holding capacity, which gives you an estimate of how long filters will last at a site. Previously, that was not listed out for all filters, but the new standard requires to be done for every single filter. We also look at hydrophobicity, which is how well the filters will perform in wet conditions and humid conditions. So for a place like Tampico, we're very close to the water, you have a lot of humidity, you have a lot of rain, that becomes really, really relevant. That's addressed by ISO 29461 Part 2. Part 4 addresses the salt performance. Again, we're close to the sea, we have a lot of coastal influence, we have a lot of fine salt particulate. Dash 4 or Part 4 of the standard addresses specifically the filter performance in those kind of conditions. Finally, we also have filter integrity. Compared to heating applications, building ventilation applications, or clean room applications, gas turbine filters need to be far more robust, and that is addressed by Part 3 of the standard. So gas turbine filters need to be really strong, make sure that they work in all these demanding conditions, and that gives you an overview of how ISO 29461 removes some of the doubt, some of the uncertainty surrounding filtration standards, and addresses all the different performance criteria for gas turbine use. So if there's any one thing you need to take away from this session is A, use good quality filters. B, if you're in a turbo machinery application, look at ISO 29461. And finally, if you have to select a filter based on that, this is a minimum recommendation. Again, we're jumping through a lot of different topics in a very short amount of time. You want filters that are at least EPA class efficiency according to Part 1 of the standard, so T10 and higher as your final filter. You want filters that are hydrophobic, especially if you're in a coastal area or area with a lot of moisture, a lot of humidity, a lot of rain, according to Dash 2, Part 2 of the standard. And you want filters that are really strong, really robust for gas turbine use, tested according to Part 3 of the standard. This is independent of ChemFil, independent of any other filter manufacturer. This is purely the International Standards Organization, ISO, that has the standard, and it guarantees that if you fulfill this, you will at least get good performance out of your assets. You will not have those degradations that we talked about earlier. Since we're short on time, I'm just going to go over quickly 2 or 3 mechanisms and 1 case study. So we talked about earlier how poor filtration can impact turbine performance due to degradation. If you have poor filtration, you get high level defouling. Because of high level defouling, you get high levels of heat rate degradation, meaning more CO2 emissions. The other way in which filters can impact performance is if they are not giving you stable performance. If your filter pressure drop, which is the resistance the compressor has to overcome to ingest that large quantity of air, if that pressure drop is high, it spikes up in salty conditions, in coastal conditions, or in wet conditions. Or if it is just overall high, you're again burning more fuel, so you're not running as efficiently as possible, and you're getting higher emissions. And finally, if you have any water going on the downstream side, again, you have degradation issues. So those are the ways, besides the efficiency itself, that the filter performance can impact your turbine and your emissions. And how that will come about is either you don't have good enough efficiency for your asset, or your filtration system is not suitable for your environment. How much time do you got? We're almost done. Okay. So I won't go into this a lot, but broadly, feel free to reach out to Jose or Antonio. There's many different kinds of filters. Some of them are suitable for certain conditions. Here again in Tampico, we're in a coastal area and a wet kind of climate. Certain filters are not really suitable, so make sure that you don't have those if you're making a new unit. And if you already have one, if your existing unit already has one of those systems that is not suitable for the site, you can also look at some other corrective actions to get better performance out of it. So I'll quickly show this last slide before we stop and take some questions. This one here. So again, it's a lot of different topics that we did not get a lot of time to go over in too much detail. Bottom line, either choose the right system from the get-go. If that was not done, and now you have an existing asset that is not suitable for the environment, you can still look at better choices for your filters. So you can look at maybe a filter, even though it's not suitable for the environment, can work in that environment. You can look at some other alternate solutions that can be added on without a major retrofit. And finally, you have to make sure that you're maintaining the system appropriately to keep it running in the right way. And last item, no matter what kind of system you choose, anytime you look at the performance over time, data is really helpful. In the long run, you should not look at the person who speaks the loudest, but the person who has the most amount of data to quantify that performance. So for all systems, we strongly recommend using some kind of remote monitoring system, so you can see how the filters are performing over time, how that filter performance is impacting the turbine over time, and finally, how does that mean in terms of your overall operations and your maintenance targets. So we do have some options and some recommendations for that. One of the things that we talk about quite often is power eye. Again, Jose's got a bunch of experience with that. We've done that on a whole lot of units in North America and Latin America. In fact, one of the case studies that we didn't go over was from Trinidad and Tobago, where we've done retrofits, and now we're also looking at remote monitoring to make sure performance is good. So, yeah, I think we're out of time, so I'll stop here, and then we'll open for some questions. I'm sorry, I ran over these things way too fast, so feel free to reach out to us afterwards.
Si nadie tiene alguna pregunta, por cuestiones de tiempo, pues se puede acercar a la logística del señor Dután. A nombre de la Secretaría, nos permitimos darle un reconocimiento y como forma de agradecimiento por participar y compartirnos su conocimiento. Muchas gracias.